Okay, so how do you estimate the latitude of the mean ITCZ in the regions of strong CEPG? Strong CEPG because there is verticity advection, and that position of the ITCZ is related to these terms of verticity advection, which we looked at in 1311, where we said the variability of absolute verticity was related to the advection of absolute verticity and verticity's vertex tube stretching and the dissipation term. For the ITCZ estimation, location estimation, assume that we are looking for a steady state inviscid case, so this term goes to 0 and this goes to 0. So then the balance is between the advection term and the vertex tube stretching term, which you can write in terms of the meridional divergent winds, because that's the main thing we are looking for, the latitudinal position. So you can ignore the longitudinal terms for now. Think of averaged over CEPG if you wish. And then the idea is that where the verticity advection term and the vertex tube stretching term balance each other is where you're going to get the ITCZ. So remembering that eta is zeta plus f, which is written as f minus dug dy in this case, a geostrophically balanced zonal wind and its meridional gradient, because dvd dx is 0 in our meridional case. So minus vd d eta dy then can be written as minus vd df partial f partial y, because the relative verticity is smaller than the planetary verticity as you go away from the equator towards the ITCZ. And we know that partial f partial y is beta, so that's minus vd times beta. You can think of that as the advection of the planetary verticity, if you will, because the relative verticity is much smaller. The vertex stretching term, vertex tube stretching term, can be written as f minus, so going back to the equation that governed v, f minus dug dy times dvd dy, so eta is this term again. That goes to f times dvd dy, because where the ITCZ is located, the shear is going to be 0, right? So then remembering that tan phi is nearly equal to phi as phi goes close to 0, so then the latitude of the ITCZ is basically approximately equal to divergent Vd divided by a dvd dy, where the divergent meridional wind is given by this equation from oops, I have to go all the way back for that, but never mind. So you can find that equation and see why we can write Vd in this way. We are looking at steady inviscid flow, so that's steady flow. That's why we end up with this. This is the dissipation coefficient, friction coefficient. dp dy is the cross equatorial pressure gradient. So you can plot this equation in terms of the divergent meridional velocity and the horizontal divergence. So you have various values of divergent meridional winds in meter per second and horizontal divergence, and equilibrium latitude of ITCZ is basically somewhere here. So the mean ITCZ as a function of the divergent meridional wind and the horizontal divergence based on this equation 13.21, not 31. Observed values of the divergent meridional velocity component and divergences at 925 hectopascal close to the surface are shown in this shaded area. Basically says that the theory is this very simple approximation is quite good. Interception occurs near 8 to 10 degree latitude, matching the observed location of the ITCZ in the regions of substantial cross-equatorial pressure gradient. Again, Lots of details, but this is not the position of the ITCZ everywhere. The energy arguments I mentioned before about ocean transport, ITCZ being the the energy equator and so on, are also valid for zonal mean. The zonal mean position with respect to the equator is determined by those calculations. So ITCZ is a big beast, has various pieces, and this is for the regions where cross-equatorial pressure gradient is very strong. Okay, so we will leave this here and look at the further details in the next podcast. This is short, but I hope you understand the point that we simplified the system, looked at the cross-equatorial pressure gradient and the divergent winds it drives, and looked at where the ITCZ ends up in that case when you have cross-equatorial pressure gradient, again with the exception of the Indian Ocean, where cross-equatorial pressure gradient doesn't drive convection north of the zero absolute vorticity line.